So after page 2, it is good to practice the questions on the right hand side first before we look at other theory. So this theory, I just hold it first. We will come back to that theory afterwards. So let's look at this question first. Okay, so now let's see. Okay, the Earth may be considered to be a sphere of radius 6.4 times 10 to the power of 6 meter with mass of 6.0 times 10 to the power of 24 kg concentrated at its center. A satellite of mass 650 kg is to be launched from the equator and put into geostationary orbit. Okay, so of course we haven't learned geostationary orbit. We just put it in this way first. That means this is the Earth. Okay, so you have a satellite here, satellite small m. So you're going to bring the satellite to somewhere which is far away, okay, which is called geostationary orbit, but we haven't learned that. Just ignore that first. So you just want to bring the satellite to somewhere which is far away, okay, and show that the radius of the geostationary orbit is 4.2 times 10 to the power of 7 meter. Okay, so how to show? Let's say this one, we ignore it first because there is a particular concept. There is a particular concept. So we don't want to care about that first. So this part A, I just ignore first. Okay, now the thing is, we focus on B first. We focus on B because I want you to build up the idea of gravitational potential energy difference. So B, we focus on B first. Okay, now you just take the value straight away, initially, okay, so you see, initially here to here is same with the radius of the Earth. So this is Ri. Okay, Ri is same with the radius of the Earth. And at the end, the satellite will reach somewhere in the outer space, which is called geostationary orbit. This is Rf. Okay, Rf. So you have to know that Ri is just the radius of the Earth, which is 6.4 times 10 power 6. The Rf is the radius of the geostationary orbit. Okay, so which means it is 4.2. 4.2 times is the value that we want to show. 4.2 times 10 to the power of 7. So now part B, they want you to determine the increase in gravitational potential energy. So how? So we just use delta U equal to m5 final minus m5 initial. So where the m is the mass of the satellite. Okay, let's say I just put everything in formula first. Okay, so this one, negative GMM R final minus negative GMM R initial. Okay, now we substitute with value. Of course, to make it easier, I will just factorize. I factorize the GMM. And this will be easier for our calculation if I factorize the G and M. Okay, so G is 6.67 times 10 to the power of minus 11. M is the mass of the Earth, which is 6.0 times 10 to the power of 24. Then minus 1 over R final. R final is R final 4.2. 4.2 times 10 power 7 plus R initial. R initial is 6.4 times 10 power 6. Okay, then we count this out, and at the end it will get 3.45 times 10 to the power of 10 joule. So this is what am I trying to let you know, where when you bring an object away, okay, then the delta U will be a positive value. Meaning that there is an increase in gravitational potential energy. So when you bring it away, there is an increase in gravitational potential energy. So that is what am I trying to say. So even our graph satisfy that also. You see our graph just now, the phi versus r graph that I draw, where I said the graph is like that and like that. Okay, so when you bring an object which is very near, you bring it away, right? Okay, you can see there is an increase in phi. So increase in phi, increase in gravitational potential. So this will happen when the graph is having a negative sign, so that's why a negative is very important, right? So when you bring an object away, then it increase, gravitational potential increase, gravitational potential energy increases as well. So when you bring an object towards the Earth, then it go the other way around, follow the black color arrow. So what happens is the gravitational potential energy decreases. So we managed to settle B already. So I mark down first. B settled already. And part A we will discuss after we go through the theory over here. Okay, so let us look at 2.5 now. Centripetal accelerations. Okay, for an orbiting satellite, the gravity provides centripetal force which keeps it in orbit. Okay, so they move in orbit because of the centripetal force. And there are two ideas over here. So centripetal force make it move in the orbit. Okay, centripetal force. So we know centripetal force is F equal to mv square. F equal to mv square over r, or mr omega square. So this is centripetal force. The other thing that we need to know here is centripetal force come from where? Come from gravity. Centripetal force come from gravity. Gravity is F equal to G m over r square. And because of that, we can equal them. We can equal the gravitational force with the centripetal force. So when we equal them, what we can do after that is we can just simplify it. For example, we can cut the m on both sides. We can cut the r we can cut one of the r on both sides as well. So end up with v square equal to gm over r. V square equal to gm over r. So what is meant by the v here? Okay, the v, yeah. So this v, it is actually the, when an object moves in a circle. So for example, something like this. Okay, this is the circular track. So when the object moves in a circle, the velocity v. Okay, so that is the velocity. Yeah. So now velocity square is equal to gm over r, and you will see that this capital M is the mass of, let's say our case is a satellite. A satellite is moving around the Earth. Yeah, let's say the Earth with mass capital M. And you see our formula is gm over r. So we just care about the mass of the Earth, and then the r, the distance between the Earth and the satellite. We just care about that. So velocity is affected by the mass and the r. So hence, they said it here, velocity is independent of the mass of the satellite. So this satellite here with mass small letter m. So it is not affecting the velocity of the satellite. Okay? The small letter m is not affecting the velocity of the satellite. So that's why they say independent. Okay, now let's move on. 2.6, geostationary orbit. Geostationary. Okay, stationary means not moving. Not moving. Geostationary orbit. Something is not moving. Okay, so it means that you see the theory here first. The first point, geostationary orbits, there's an equatorial orbit. Equatorial orbit. So what is meant by equatorial orbit? Right here, it is the orbital path which is directly above the equator. Directly above the equator. So you have to know what is equator. Equator is, let's say, this is the Earth. Equator is the one in the middle. Okay, so that is equator. This particular circular track in the middle of the Earth is the equator. So of course, Malaysia is somewhere around the equator. Okay, then what is equatorial orbit? Equatorial orbit, let's say I use blue color. So it is an orbit which is just above of the equator. So something like that. So this blue color track that I drawn here, I drew here, is the equatorial orbit. Okay, equatorial orbit. So now period is 24 hours. Same angular speed as Earth. Earth spins one round in 24 hours. Okay, so then the geostationary orbit, they say period is also 24 hours. So what is meant by that? So you imagine, let's say today Malaysia is launching a satellite to the geostationary orbit. Let's say our TV company, Astro is launching a satellite to the geostationary orbit. Of course, the purpose of Astro, which launched the satellite, is to serve the is to serve the country, to provide the TV signal to the to Malaysians, so that they can watch TV from Astro straight away. Okay, so in that case, right, we know that the Earth is spinning. Okay, and the satellite must always stay above of Malaysia. Okay, so imagine that at one moment, Malaysia is here, located here, and then the satellite have to be just right above Malaysia. So at the moment when the Earth spin and until it reach the other side, let's say it reach here, we have to make sure that the satellite is still above of Malaysia. Okay, so that is what we call the geostationary orbit, where the satellite have to move at the same speed, same angular speed with the Earth. Okay, with the angular speed of the Earth, so must be the same. So because of that, period is 24 hours. So that means when the Earth spin one round in 24 hours, the satellite also spin one round in 24 hours. Okay, they have the same angular speed, and because of that, it is always above of the same place. Okay, the same place that we are launching. Okay, now from west to east, the next point, from west to east, same direction of rotation as the Earth. Okay, so we have to know the Earth spin from west to east. Okay, so meaning that it is like this. Let's say we draw it up. Okay, this is the our compass: north, east, west, and south. Okay, from west to east means the Earth is spinning this way. Let's say I draw the axis here. Okay, it's spinning this way. So if it's spinning that way, right? So imagine let's say the sun is here. The sun is here. So what happened then is country in, let's say, Japan, they will get the sun first. Okay, country in Japan will get the sun first, followed by country in other parts of Asia like Malaysia, so that we get the sun later, and then Europe will get the sun much more later, and followed by United States of America, so that will get the sun at the end. So if you understand that kind of concept, right, that means we have to know that the satellite which is launched from Malaysia, let's say the Astro satellite just now, so it has to move in this direction also, west to east. Yeah, west to east. They have to move in that direction so that it is always above of the country. So we want something like that. Okay, so that is geostationary orbit. The important thing is the period is 24 hours. So this is very important. How important is it? For example, you try to understand it in this way. So something like this. Example. Centripetal force is equal to mr omega square. Okay, mr omega square, where omega is the angular speed. And we also know that omega is the angular displacement over time. So now, when you have that information, where the period is 24 hours, to move one round, the time span is period. And to move one round, the angle is 2 pi, which is 360 degree. Okay, so the theta is 2 pi. The time is 24 hour. So where we get 24 times 60 to change it to minutes, times 60 again to change it to second. So by doing this, you will know the omega, the angular speed. We can count out the angular speed, and after that we can count out others, like maybe we can count out the centripetal force at the end. So at least the period of 24 hours help in this sense. Okay, now let's move on to the next part. The next part is geostationary satellite. So geostationary satellite is one which is always above a certain point on the Earth. on the Earth. So that is the satellite that I mentioned just now. It's always above of Malaysia, for example. Now, the next point, for a geostationary orbit, t equal to 24 hours, an orbital radius is a fixed value from the center of the Earth. So it's a fixed value. So that means we can count it out. We can count it out and find out the R. Okay, we can count out and find out the R. So imagine that we can make use of this formula again. This formula, the gravitational force is equal to the centripetal force. So imagine these two are equal. So it's something like this. Okay, let's say I do it at the side here. Gmm over r square is equal to centripetal force. So we know centripetal force, there are two versions. As you can see up here, mv square over r is centripetal force. mr omega square is also centripetal force. So let's say now, because we already know omega, so let us use this then. Okay, so we use mr omega square. We cut the m. Then we want to count the r. R is a fixed value. So imagine that I continue doing this. I rearrange the equation. Gm over omega square equal to r cubed. R equal to cube root of Gm over omega square. So by doing so, right, we can find the r. So the r here is not the radius of the Earth or whatever. It's the distance from the center of the Earth to the satellite. Okay, let's say I put it in black color, from the center of the Earth to the satellite. Let's say the satellite is there. So this is R in black color. So you can find that it is a fixed value. So why is a fixed value? First, G is a fixed value. M is the mass of the Earth, which is a fixed value. Omega is fixed already, which is 2 pi over 24 times 60 times 60, which is also a fixed value. And then you cube root, then you get a fixed value of R. It is always constant, as all these things are constant at the other side. So that's why they said radius is a fixed value. Okay, now let's move on. However, mass of the satellite is not fixed. Mass of the satellite is not fixed. Hence, the Ke, GPe, and centripetal force are not fixed values. So it means that first, they said mass of the satellite is not fixed. So imagine that the satellites have human beings inside, let's say, for example, and the satellites have some fuel. Okay, so they use up fuel, and then the satellite become lighter. So that's why the mass of the satellite is not fixed. That is one scenario which makes the satellites to be not fixed. It has fuel inside there. Okay, then the other thing is, hence, the kinetic energy is not fixed. This is reasonable. Let's work it out here. We know kinetic energy is 1 over 2 mv squared. So where m is the mass of the satellite. So it is not fixed, and hence kinetic energy is not fixed. Kinetic energy is not fixed. Then okay, so at the meantime, you have to be careful a bit. We say kinetic energy is not fixed because m is changing. But don't forget that v is constant here. You look at the formula up here. V square equal to gm over r. G is a constant. M is the mass of the Earth, which is a constant. R just now we already discussed. They said radius is a fixed value. So this is also a fixed value. So Gm over R is fixed. And then V is hence a fixed value also. It's a fixed value. So V is a fixed value. Velocity is the fixed value. But because of the M, which is not fixed, which is changing, so kinetic energy is affected by the M, not affected by the V. The V is the same all the time. Okay, so that's the thing. GPE, GPE is also not same. GPE, okay, let's take a look. What is the formula of GPE? So GPE is actually equal to M phi final minus M phi initial. So the M here is not fixed. Okay, so because of that, GPE is not fixed also. So that is the thing. And centripetal force are not fixed values. Centripetal force, okay, let's see. Centripetal force is mv squared over r equal to mr omega squared. So it's not fixed also because of the m. The small letter m there, which is not fixed, and makes centripetal force not fixed. Not fixed. So these are the three things that are not fixed: kinetic energy, GPE, and centripetal force. They are not fixed. So what is fixed is, okay, let me put it in this way. The one that I circle in green is not fixed. So KE, GPE, centripetal force, these three are not fixed. So what is fixed is, let's say I circle it in blue color. The R is fixed. And then the other thing is the V. The V on top of the screen. The V is also fixed. So these two are fixed in blue color, and these three are not fixed. Okay, so let's move on. A geostationary satellite is launched from the equator in the direction of rotation of the Earth. Okay, so west to east, that means west to east. So that means when you launch, let's say this is the place that you are launching the satellite. So you have to launch from west to east. From west to east. That means something like to the right, then they reach the track of the geostationary orbit, then they keep rotating. So they will just rotating around the Earth because there is a gravitational force that attract, and hence it creates centripetal force. So that the axis of rotation of the satellite and Earth coincide. So that means the satellite move in this way, where the center of the circle is this axis. The Earth move in this way also, where the center of rotation or the axis of rotation is that same line also. That is meant by coincide, same line. Okay, so we have done. And now let's see the questions again. But we are going to look at part A only. Part A. So, okay, what they ask here, show that the radius, we see part A straight away. Show that the radius of the geostationary orbit is 4.2 times 10 to the power of 7. Okay, so this is what we discussed just now, saying that R is a fixed value. Okay, so the discussion is done just now at this particular part. Yeah, GMM over R square equal to MR omega square. So we are doing this, and now let us just substitute value. Okay, substitute value. But of course you have to show working, So you have to show GMM over R square equal to MR omega square. Then you cut the small letter m. Then you find R cubed equal to GM over omega square r equal to cube root g m over omega square. Okay, now we substitute value. Cube root of, okay, first start with g. So g is 6.67 times 10 to the power of negative 11. The capital M is the mass of the Earth, which is given here. 6.0 times 10 to the power of 24. So we just put this in our formula. 6.0 10 to the power of 24. So at the bottom we have to count omega. So the calculations of omega I already showed just now in the Earth. On the left hand side. Omega is 2 pi over t. T is 24 times 60 times 60. Yeah? So that is omega. So now we put that value at the bottom. 2 pi over 24 times 60 times 60. Then we square it. And by doing so, we press calculator and you will get 4.2 times 10 to the power of 7 meter. So we managed to show the value. Yeah? So it's a fixed value. So you just need to memorize up the working and just work it out accordingly.